Good evening, Year 11, and welcome to the third of 4 catch-ups GCSE Chemistry sessions. As I hope you can now see that the session tonight will be giving you an insight into the extraction of metals. So as always, I will be available to answer any questions you have, so feel free, if you've got any questions, to post them in the Q&A section, as we always encourage you to do, and I will get back to you. And I will hand you swiftly over into the safe hands of Mr. Black, who will be leading the session tonight.
Okay, so good evening, Year 11. I'll be going through the extraction metals, as you can plainly see. So let's begin. So extracting metals, always start when I talk about metals, these sort of metals here. So we've got gold, the biggest nugget of gold that's ever been found, I believe. I imagine that's a fake. We've got some platinum, we've got some silver, and we've got some copper. So these metals, we all refer to them as being native metals. Okay, so why are these metals what we call native metals? Well, extracting metals is intrinsically linked to this thing here called the reactivity series. You don't need to know the reactivities of these metals as such, okay, because you can infer it. But it is useful to kind of know their relative reactivities, and it's just really useful to know that gold and platinum and silver are towards the bottom. All right, so these metals are what we call native metals. However, if you just look there, I'll just go back a slide. You can find silver as a native metal, although it's quite rare to find it as a native metal. You normally find it as an ore, and you would have to extract the metal. It's quite easy to do though, with it being so low in the reactivity series. And the same with copper. I mean, you can find copper natively, i.e. it belongs in the soil. It is native to the soil, okay? Although you will quite often find it as the ore. And if you look, it's quite nice actually. You've got a copper nugget, and you can see here already, due to its relatively high reactivity compared to gold and platinum, it has started to react. So what makes these native metals is their low reactivity, their unwillingness to combine to other substances. Now, iron. Let's talk about iron. Is smack bang in the middle of the reactivity series. Would we find that as a native metal? The answer is no. Oh, and by the way, this is more likely the way you'll find copper. This is the ore malachite. So would we find iron as a native metal? The answer is no. You wouldn't find it. You would not find it in the Earth's crust as the metal. We wouldn't dig it out of the ground. However, you can find meteorites that are composed of iron, but these would very quickly react with the Earth's atmosphere, and you'd probably form iron oxide. Okay, so the point is, most of our metals are going to need extracting, and that's going to involve some chemistry. So this session really is about the type of chemistry we're going to use to extract these metals, and the method we use is linked to the reactivity series. So I've got two ores here. So an ore is a rock that contains enough of a metal to make it worthwhile extracting. So we've got an ore here. This is copper ore. You can see the green colour of the copper. Right, so this is called, the actual ore is called malachite. And here we've got iron ore, and you can see the characteristic colour of iron, this reddy brown colour that we associate with rust, iron oxide. Okay, so the first way we're going to extract these metals, copper and iron, is using some classic old chemistry. We're going to use carbon, and hopefully by now you're familiar with the role of carbon in extracting these metals. Okay, so here you can see carbon in the form of, which we can get in the form of coal or charcoal. You can also get the carbon from wood. Okay, so you can turn your wood into charcoal. Our main source of carbon though is coal. Okay, so I did say you need to know, or you should be familiar with the role of the carbon. So you can think of it in two terms. You can think of it as being involved in a displacement reaction, or you can think of it in terms of chemical reduction. And we're going to explore both of those meanings now. So we'll start off then with displacement. So it's key that you are able to predict when a displacement reaction is going to take place and what the products of that displacement reaction would be. So we've got two substances here. We've got iron as the element, and we've got copper, but it's chemically combined. So displacement, hopefully you know, is where a more reactive metal takes the place of a less reactive metal in a compound. And therefore, you can see here how the iron has displaced the copper. So we end up with iron sulfate and copper metal. Iron can only do this because if we go back to our reactivity series, iron is above copper. Okay, so you can see the iron here in the reactivity series. That's why it was able to displace the copper. Now you'll notice carbons here for a very important reason. Let's look at this one then. Would we get a displacement reaction here, and what would be the products? I'll just give you a moment to reflect. So hopefully you've decided yes, there would be displacement. We've got magnesium above the iron, and hopefully you predicted the products would be magnesium sulfate and iron. So you can see here what we're doing is we're extracting a metal using another metal, a more reactive metal. Okay. If we tried to do this reaction then, would we get displacement? So I'll give you a moment or two just to reflect. And hopefully you can see that there would be no reaction due to copper being less reactive than the iron. The copper is unable to displace the iron. So here's a question for you to think about. Zinc reacts with iron sulfate but doesn't react with aluminium oxide. List the metals in order of reactivity. So have a little think. When I say reacts, what we're saying is displace. Okay. Hopefully you've worked out the reactivity series as that. Iron would be at the very bottom here. It's displaced by the zinc. Zinc's in the middle because it can't displace the aluminium. Okay. So that's a typical kind of thing you might be asked to at GCSE. Look at some reactions, and from those reactions work out the relative order of reactivity. So something to look at here. This is what we might see in a displacement reaction. You can see we've got an iron nail, and we've got this in copper sulfate. This is how it starts, and this is what we end up with. Now, interestingly, and hopefully you know, this blue colour is characteristic of copper. This links in directly to your work on acids that was presented last week. It's well worth knowing the colour of copper solutions being blue, all right, because quite often it's an observation when we talk about acids and reactions. If you form a blue salt or blue solution, it's a copper solution. In this case, it's copper sulfate. And if you look to the right hand side, we can see this change in colour, right? And I'm just going to put something out to you. This red brown solid that's formed on the nail is not rust. Okay, the number of times I see people identify a red brown solid in this reaction as being rust, I've lost count. This is the copper we're displacing. So you'll always see a solid forming. Whatever that solid is will be the metal that's being displaced. Also notice as well, please, the colour of the solution. This is important later when we look at the colour of our transition metal complexes. Copper, as we said earlier, is a blue colour. This is copper 2+ ion. And here, the green colour is associated with iron 2. So we'll come back to that a bit later. Okay, this is a very important, another example of a displacement reaction. You can see here, aluminium, which is more reactive than iron, has displaced the iron. Okay, and we've got a little symbol equation here. And I would highly recommend that when you go into any of your assessments, you are familiar with your ion sheet. It was taught to you in year 10. It's crucial for year 11. You've got to be able to write the formula, something like iron-free oxide or aluminium oxide. So you will, in your assessments, be provided with an ion sheet, and you will be provided with a periodic table. if they are required for that particular assessment. Okay, so just to point out why this is an important reaction, this is actually highly exothermic. Hopefully you know that term means releases releases heat. And you can see here that the heat is sufficient to actually melt the iron. And this is why the thermite reaction is used to weld railway tracks together. So the reaction takes place in this vessel. They start with aluminium oxide powder, iron oxide powder and aluminium powder. They light a fuse, they step back, and after the reaction is completed, they let the molten iron pour out the bottom. So, using displacement to extract metals, we wouldn't displace a metal with a more reactive metal. That would not be economical. All right. So what we use carbon. Okay. And the reason we use carbon is because iron is less reactive than carbon, so carbon can displace it, and also carbon is extremely cheap and abundant. So the overall process, we could simplify this reaction as below. You can see there I've got my iron oxide and carbon, and you can see that the carbon has displaced the iron. All right. So as you remember earlier, we said carbon, we source that from coal. We have to process the coal, purify it before we use it, but yeah, that's your main source. Okay, now this brings us on now to a very important term. I did mention it earlier. I talked about how the carbon is displacing the iron, but we also can say that carbon has reduced the iron oxide. So you have to have this good understanding of these two terms, oxidation and reduction. So the word reflects the process, and this is what we find in chemistry. So oxidation, you've added oxygen. So you can almost read it as oxidation, and reduction.
I'm not sure whether this is me or whether it is across everybody, but I appear not to be able to hear you anymore, Mr. Black.
Say all the time is they will say that the iron is being reduced, and I can see why they're saying that, but iron isn't being reduced. Iron oxide is being reduced. So please make sure when you are identifying who's being oxidized or reduced, refer to something on the left hand side of the arrow. All right, it's got to come from the left. So iron oxide is being reduced to iron, and hopefully you will identify that the carbon is being oxidized to carbon dioxide. Okay, so on that basis, have a quick look at these three reactions. I won't give you long because we're doing a live lesson. We've got not a great deal of time to cover quite a lot of content, but you can always play this video back if you need to. But for the moment, just have a quick look. So we're trying to work out what's being oxidized, what's being reduced. So I look at the left-hand side of my equation, and I can see here, I'm going from copper oxide to copper. We've removed oxygen. Copper oxide is being reduced. The hydrogen is gaining oxygen, it's being oxidized. In this reaction, these are all reactions that take place, by the way. Here we can see the magnesium is being oxidized, so magnesium oxide, and the water is being reduced to hydrogen. And this equation here is vital for the exam or any assessments. I would always stress to my pupils for a GCSE exam to make sure they're familiar with this equation. You can see again the iron oxide is being reduced to iron, and the carbon monoxide is being oxidized to carbon dioxide. Okay, so this is being reduced, and it's being oxidized. And this, you know, explains why we refer to these processes as being redox processes. You can't have one without the other. If something's being oxidized, something has to be reduced, and vice versa. So the next bit we're going to talk about then is, you know, the actual chemistry, the process, the industrial process. So hopefully you know that we extract iron using carbon in something called a blast furnace. So let's look at what a blast furnace looks like. So a common thing you'll be asked to do in an exam would be to label a blast furnace. So you'll be given something like this. You may not have actual arrows indicating things coming in or coming out. So just very quickly, I'm going to show you what goes in. So you need to know the blast furnace, and you also need to know the roles of those materials. So we've got 4 raw materials. 3 of them come in at the top. We've got the iron ore, we've got the coke, which is the form that carbon is in, and we have the limestone. You need to know the role of all 3 of those. The other raw material, a lot of people don't see it as raw material, but I guess it is a raw material, is hot air. And this is blown in towards the bottom of the blast furnace. Okay. Now, the rest of the pipes are where things are coming out. So very bottom of the furnace is your molten iron. This is where it collects. It's molten due to the heat, and being dense, it sinks to the very, very bottom of the blast furnace. Just above your molten iron, you then have this stuff here. This is called slag, or it's the waste products from the blast furnace, and we'll be looking at the chemistry of its formation in a moment. And finally, we've got the pipe here. This is your exhaust gases. All right, so it's mainly carbon monoxide, carbon dioxide, and interestingly enough, they tend to use this stuff to heat the hot air. Okay, so stuff that come out of the furnaces will then be used to heat the hot air going into the furnaces. Okay, the roles. The coke has 2 roles, and a lot of people only think of 1 role, but it actually has 2, and you quite often will be asked to know or know both. So the first one is to take away the oxygen, to displace the iron from the oxygen, to chemically reduce the iron oxide. The other role of the coke, though, is it actually burns in the process, and in that burning of the coke, it produces lots of heat, which is what we need for our extraction to take place. So it's got 2 roles. Number 1, to chemically reduce the iron oxide, and number 2, as a fuel. Then we have the limestone, and this is to remove your acidic, sandy impurities, and they remove that as something called slag, okay, calcium silicate. And as I say, we'll look at that chemistry as well. Okay, hot air, that's to get the coke to burn. All right, so it has to be hot to get the coke to burn. So we'll talk about the slag in a moment. I'll just leave that there for you. You can see it floats so on top of the iron because it's less dense. So the chemistry of the blast furnace. This is where you need to be able to explain the processes. So first thing that happens is we are constantly filling this blast furnace with what's called a charge. And the charge is the coke and the limestone and the iron ore. Now, like I say, I'm going to treat the limestone separately because that's for the formation of slag. We'll look at the carbon and iron oxide. Okay, so you can see our carbon and we can see our iron oxide, and you'll notice the blast furnace, it's extremely hot at the bottom. Okay, so the first thing that happens is the hot air is blown in, and this reacts with the carbon and it forms carbon dioxide gas and lots and lots of heat. Now, being a hot gas, the carbon dioxide rises at the furnace and it reacts with more carbon to form carbon monoxide. Now, I'm just going to stop there for a second, and I'm going to ask you to think about this as a redox process, this step here. What's being oxidized and what's being reduced? Okay, so hopefully you'll identify that the carbon is being oxidized to carbon monoxide and the carbon dioxide is being reduced to carbon monoxide. And what's happened here, this carbon has taken one of these oxygens from the carbon dioxide that formed down here. Right? This is oxygen rich, there's lots of oxygen down here for carbon to react with, and here it's oxygen poor. So the carbon here takes one of these oxygens. You could see the carbon dioxide is being greedy, so the carbon takes one. And we form 2 molecules of carbon monoxide, and this is primarily what reduces our iron oxide. So it is carbon reducing the iron oxide, but it's in the form of carbon monoxide. Okay, so final bit, there's our reaction, and you can see here each carbon monoxide takes one of these oxygens to form our carbon dioxide. That's why we need 3 carbon monoxides, 1 for each of the oxygens. So quite simple chemistry going on there, but you know, you definitely worth having perhaps another look through that slide. Now, this is just straight off the syllabus. These blast furnaces run 360 days a year, 24/7. They don't turn them off. Once they're charged and going, they're kept going. And the reason for this is that well, you can see there, it's just so expensive to start them up again. Okay, it takes a lot of time. And also, could you imagine having a furnace full of molten iron, well, solid iron, the slag solidified and the charge? You pretty much have to build a new furnace. Okay. So, like I say, that equation, you must know it for the blast furnace. Okay, and we'll just balance it there. You can see the carbon monoxides that have reacted, that formed in the furnace. Each of these needs to gain 1 oxygen to become carbon dioxide. Okay, so you need 3 of them. And you form your 3 carbon dioxide. So definitely worth perhaps writing that down and looking at it on a regular basis. Okay. And there's your equation as well, also worth knowing. So this is the formation of carbon monoxide. 2 equations for the blast furnace that are worth knowing. Now this formation of slag, you don't see it assessed much. The only way I tend to see it assessed is what is the role of limestone. And the role of limestone is to remove acidic sandy impurities. Now it is on your syllabus, so I will go through just the basics of it. Okay, so when you put limestone into the furnace, limestone is actually a chemical called calcium carbonate. And when it gets hot, it undergoes a reaction known as thermal decomposition. Now, if you're doing triple award, you should be familiar with the role of limestone, and you should be familiar with the term thermal decomposition. If you're doing double award, you don't need to know it's called thermal decomposition, but you do need to know that the calcium carbonate becomes calcium oxide. This is what we call lime. And lime, hopefully from your lesson on acids, you'll recognise as being a base. What is a base? Well, a base is a metal oxide or a metal hydroxide. And here we've got calcium, a metal oxide. So this is a base. And a base will neutralise an acid. So if we look at iron ore contains lots of iron oxide, but it also contains lots of a chemical called silicon dioxide, better known to you as sand. So silicon dioxide here is sand. So it shouldn't come as a surprise to you that most rock is sand. Okay, and obviously we don't want sand in our iron, so we need to get rid of this sand. Now silicon dioxide is acidic. So what happens is, believe it or not, there's a neutralization reaction. The lime, the calcium oxide, neutralizes the acidic sandy impurities. And this stuff here, calcium silicate, that's the chemical name for the slag. That's what we collect above the molten iron. So, as I say, you don't tend to be asked it. The only thing you do tend to be asked is what's the role of the limestone, and as I say, that's to remove the acidic sandy impurities, and that's the chemistry that's involved. Now, I'm just going to whiz through this bit of the slide because I want to get onto electrolysis. I'm going to leave it here for you. it's the iron to steel. So iron is, wait a second, thank you. Iron, when it comes out of the blast furnace, has too much carbon in it, and that makes the iron very brittle. So what they do is, to convert iron into steel, they remove the carbon. Okay, so it's cast iron to steel. And I'll just leave that there for you. Cast iron is actually very useful as a metal for certain roles, but if you want any form of malleability, you have to reduce the carbon content. And you get various grades of steel. You can have, mild steel, which has got quite a lot of the carbon removed, but not all of it. And that's good for making car panels. And then you have things like wrought iron, where there's very little carbon in there, and it's incredibly malleable. So I'll let you look at that bit yourself, because I want to look at this part, which is where we have metals that are more reactive than carbon. We can't use displacement. And the best example really here to talk about is aluminium. So we know aluminium is above carbon in the reactivity series, so we're not going to be able to use it. Displacement with carbon or chemical reduction with carbon. So we have to use electrolysis. And it's really, really important here that you know that to carry out electrolysis, the substance you're using or extracting the metal from has to be molten, which means melted, or aqueous, which means it's been dissolved to form a solution. It's also worth knowing that electrolysis uses electrical energy. Okay. So we have some really, really important terms when we talk about electrolysis, but what I think I'll do is I'm going to come back to those in a second. The cat will make sense in a minute. What I'm going to do is I'm going to look at something like aluminium oxide. If I wanted to extract aluminium, as I say, we have to carry out electrolysis. So to do that, the first thing I do is I connect up some graphite or carbon rods to a DC power supply, direct current. Alternating current wouldn't work for electrolysis. Hopefully you know with an alternating current, our electrodes, which are these rods sticking into our aluminium oxide, their charges would be swapping constantly. So one would be plus and then it would become a minus and so on. Okay, so we're going to use a direct current. If you think of direct current, I always think of a battery. A battery has a positive terminal and a negative terminal. So I connected this up to a DC current. I made this rod positive, this rod negative. Let's say these rods are conducting, so they're usually made of carbon in the form of graphite. And I want us to think about aluminium oxide and what aluminium oxide is, what kind of compound. Well, if you're present on the bonding module, you know you've got a metal combined to a non-metal. So hopefully you'll understand that aluminium oxide is ionic. And we call this aluminium oxide the electrolyte. All right, so whatever you are going to be splitting up in electrolysis is called the electrolyte. And as it's ionic, if we melt it or dissolve it, it can split up into its separate ions. And again, you know, if you're in the exam and you haven't got your ion sheet, ask for an ion sheet because you need an ion sheet. So aluminium oxide is made up of two ions, the aluminium ion, Al3+, and the oxide ion, O2-. And it's the fact that it's ionic allows us to split it up using electrolysis. So there's a rule in chemistry that opposites attract. So this ion here, the positive ion, will be attracted to this negative electrode, and this negative ion would be attracted to the positive electrode. So we're effectively splitting them. It's a little bit more complicated than that though. So I'm going to introduce you now to the key terms, and hopefully you'll understand why we had the picture of the very cute kitten. This is the way I remember all of my key terms in electrolysis. Cation. Cation is the, and it's not a misspelling, it's the positive ion. So I'm just going to scroll back and you can see why I have my picture of a little kitten. All right, because whenever I think of electrolysis, cation comes to mind straight away, and I know cations are positive ions. Okay, and that helps me then with all my other key terms. And we'll come back to those key terms in a minute. There's aluminium oxide. We've melted it or dissolved it. That allows the ions to become mobile. We call the positive ion a cation. And as I said earlier, this cation will go to the negative electrode. Okay, so you can see it's being attracted to its opposite charge. And when it gets there, oh, by the way, yeah, I meant to say that. So there goes your cation, its positive charge. The electrode it goes to is the negative electrode, so we call this the cathode. All right, so you have the cation goes to the cathode. So if ever I can't remember the charge of the cathode, I always go, right, charge the cathode. Cations go to the cathode. Cations are positive. The cathode must be negative. What happens when it gets there then? Well, why has it got a 3+ charge first of all? Well, it's got a 3+ charge because when it reacted, ionically bonding, it lost 3 electrons. So what we're going to do is we're going to give those 3 electrons back. So don't worry about the reading. Please don't feel you've got to keep the reading there. The PowerPoint will be made available to you and you can read these things at your leisure. I'm talking you through them. So you can see there, what I'm doing is I'm returning those electrons that were removed during ionic bonding. We're returning them so we have the aluminium atom. Okay. So that's the aluminium dealt with. Now you also need to be able to know what's going on at this other electrode. So let's see what this ion's called. The positive ion is the cation. This ion is called the anion. All right, the negative ion is called the anion, and it will go to the positive electrode. Opposites attract. Okay, so let's look at what's happening at this electrode. The electrode it goes to, because this is the anion, we call it the anode. And what happens at the anode? Well, as we say, the anode, which is our positive electrode, will attract these anions. And we can see they've got this -2 charge. So what I've got here is a dot and cross diagram, or part of the dot and cross diagram. And we can see that these electrons have come from these aluminiums. They have extra negative charge. And in the case of the oxide ion, it's a -2 charge, or 2- charge. So it's got too many electrons. And what we are going to do, you see there, is we're going to remove them. Okay, so we're going to take those electrons away. And this is what happens at the anode. So we remove those electrons and we form O. Now there's a slight complication here in that oxygen is always written as O2. All right, so we never write oxygen in equations as O because it doesn't exist as separate oxygen atoms, it exists as a diatomic molecule. All right, O2. So we're just going to balance that up. So the first thing I'm going to do is I need 2 oxide ions. Okay, so I have 2 of them, so I can have O2. And from each of those, we're going to remove 2 electrons to get rid of the charge. So altogether, we'll be taking away 4 electrons. This equation, you have to know it. Okay, it is part of your, it's actually mentioned on the syllabus. Okay, so I've just added that there for you. If you, when you come to do the PowerPoint yourself, there's an explanation of the charge and also the formation of the oxygen. Okay, so just very quickly, this is how it's done in industry. Okay, so you have these, you know, it looks a bit different to a beaker with 2 rods sticking in them, but the process is the same. You have your anode and your cathode. Notice the charge of the anode, please, the positive charge, and the cathode has got the negative charge. Remember, cations are positive, they go to the cathode, negative. Okay, and it's worth knowing, you know, that these are made of carbon. Okay, carbon conducts electricity in the form of graphite. And there's a couple of things you need to know about the process. At the anode, this is where our O2- will go. Okay, so our O2- will go here, and it will form oxygen. Now, this cell is very, very hot. And the reason it's hot is to keep the aluminium oxide molten, right, in its molten form. So it's very hot, we're forming oxygen at it, and what tends to happen is the anode will burn away. So it has to be replaced on a regular basis. I think it's every 28 days they're replacing anodes. All right, so it's at 900 degrees C. And the reason it's so hot is the aluminium oxide has to be molten for electrolysis to work. Now, keeping something at 900 degrees C for a long amount of time, pretty much all year, is going to cost you a lot of money. So, but could it be even more expensive? Because actually aluminium oxide has a higher melting point than that. But what's done in electrolysis is they use this stuff here, it's called cryolite, and that's used to lower the melting point of the aluminium oxide. Why does it have to be molten? Well, hopefully you appreciate from your bonding topic, if it's a solid, the ions can't move. Right? Your ions can't move to the electrodes in a solid form, so we have to keep it molten. So here we come on now to redox again. Now we've already talked about redox, but we talked about it in the context of losing or gaining oxygen. We can also talk about it in terms of electrons. All right, and when we talk about electrons, we've got a little thing to help us remember which is which. It's called oil rig. All right, oil rig stands for oxidation is loss of electrons and reduction is gain of electrons. Okay, so oil rig is a really handy way of remembering it, but don't use it for oxygen. It's only used for electrons. Okay, so if we look at this process, what have I done there? There we are, that's okay. So you can see here, this is what's happening at our anode, okay? And you can see that the oxide ions were losing electrons. So we would say that the oxide ion, or this represents oxidation, okay? And here, this is a positive ion, a cation, it would be at the cathode. And you can see here that the ion is gaining electrons. So we would say here this would represent reduction. Okay, so taking away electrons, loss, oxidation, adding electrons, reduction. Okay, so there's a good video there that you can follow if you have the PowerPoint. And then just very quickly, I'm just going to go for these because we've only got a few minutes left. The rest of it, I've talked about the chemistry. The rest of it I've left on the PowerPoint for you to just read through. You don't really need it explaining, you just need to know it. These are the reasons we cite a plant where we cite them. The main one being the access to the electrical supply and the deep sea port. All right. And the rest I say, you can read through. So we've got reasons that we need to recycle materials. And I'm just going to show you as well here what's on the rest of the PowerPoint. We've got the uses and properties of these materials. So the main use here we can see is the resistance to corrosion. Please don't say we use aluminium in greenhouse frames because it has a low density. Greenhouses don't have to float, but we do have to stop them corroding. Okay. These are good uses though for the low density. So you've got like bike frames, aircraft, climbing gear. These cables in electricity cables have got aluminium core, so good conductor of electricity, and it also has a low density, so you can have bigger spans between the pylons. Like I say, this is all here on the PowerPoint. Copper, best thing for copper, it's good at conducting heat, so obviously for cooking, and also on heat sinks. All right, so you can get the heat away from the processor. And obviously, it's good at conducting electricity. And of course, in cabling as well, it's got to be very malleable. Cables need to go around corners. And copper as well, being low reactivity, makes it good for water pipes. And then we've got titanium. The most important use, I guess, for titanium in for the exam would be as artificial joints. And the reason it's so useful is A, it doesn't corrode, right? It's got this resistance to corrosion. And also it's incredibly hard, which means it's not soft, which means it won't wear away with that continual movement in the hip joints. And we've got things like rotor blades and helicopters. Obviously, it's got to be incredibly strong and low density, and we don't want rusty rotor blades. Okay. And you've got your jewellery as well, increasingly used. Okay, and then finally, just to talk to you about the transition metals. These are in the middle of the periodic table. Okay, so it's worth knowing. Typical properties, you know, high melting point, high boiling point, things where you would associate with metal. However, there are special properties. Okay, the first one you need to know is they're very good catalysts. All right, now from year 10, you may know or may not know because of COVID. That means they're good at speeding up specific chemical reactions. So, for example, you have platinum for making ammonia. They speed that reaction up. And this links us back into our form earlier. They have what's called variable oxidation states. So you can have one more form of one ion. Here you can have ion 2 or ion 3. The ion here has lost 2 electrons. This ion has lost 3 electrons. And finally, we've got the coloured compounds. So you quite often see transition metals used in things like glazes. So you've got here, I think this is probably going to be copper, or it could be chromium. And you need to know those colours. Okay, so you remember earlier with our displacement reaction with the copper sulfate, had that blue colour, and during the reaction, it ended up with this green colour, the iron 2 sulfate. So that's your topic on extraction of metals. As I say, it's not all of the topic, in that I've not talked you through all of it, but it is available on the PowerPoint for you to have a go through and read yourself for the uses of things like copper and titanium. All right, thank you. I hope that's given you a bit of insight. And next week, I think we're looking at crude oil, which will be very useful for you. Thank you.
Yeah, thank you. Just to clarify, we are indeed doing crude oil next week, and just a quick apology, and it is entirely my fault, not Mr. Black's, but I think we might have started the session slightly earlier than what we'd intended to do. So if you missed the beginning of it, then please do go back and watch the recordings. As always, they are available to you. Okay, so thank you very much, and we'll hopefully see you next week.